Let's get going.
Loosen up, bit of lunges.
Lunges.
Action. There you go. Just do it. Just
Right.
go with the flow of the lunges, Mark.
We're back.
Welcome back. It's round 2 of A-level chemistry.
We are still at Unit 1. Just a quick recap of last video. It was mostly about moles and
And equations.
This time it's going to be primarily about acids and bases
But
reactions.
first, we're going to put something we didn't really go over last time. It's a small thing that comes along in chemistry. Empirical formula.
It's on page 12 if you have the book that we have. So this didn't really fit in quite easily for us to explain last time with all the moles and stuff, so we leave it out and put it in this video. So we're actually backtracking slightly in terms of the book, but Unit 1, empirical formula, it's a definition you've got to know.
It is. What empirical formula is basically the simplest molar ratio of a compound. So we're going to go through a few examples and how to work out some of the questions that might come up.
Alright, so could you read me worked example number 1? We're working from here if you have the book. I'm just going to quickly go through this and what we're doing.
Right, so, well then.
Yeah.
Analysis showed that 0.6075 grams of magnesium combines with 3.995 grams of bromine to form a compound.
And what we have to do in this question is work out the simplest molar ratio between magnesium and bromine. So what do we have to do, Triv?
Well, first you have to look at our periodic table, find out the AR of each of these things are. So for magnesium it is 24.3 and for bromine it is 79.9.
Okay, that's in your periodic table. So then what do we do next? What's the next step?
Well, we look at the two things, we divide the amount of grams we have of each of these.
You'll notice it's actually like the mole equation, mass over molar mass.
Yeah.
It's essentially what you're doing.
Because it's the simplest molar ratio, so you're finding how many moles of that are how many moles of that. And 3.9. Yep. Divided by 79.9.
So what are the answers of these? I don't have a calculator on.
0.025 on the left and 0.05 on the other side.
These are quite nice numbers. They work quite nicely.
They do. So what you do next is you divide both sides by the smallest number.
Which is this one.
Yep. And you'll see that that goes into that twice.
Yep. So dividing by the smallest number, dividing by itself, is just going to be 1.
And
It's a ratio, so I'm putting the ratio dot.
like baking.
That divided by the smallest number is 2. So we have 1 to 2, which means we have 1 magnesium to 2 bromine, which can be written like this.
Means you give the
Okay.
dodgy pen.
I like it. MgBr2.
And if you know a bit more about charges of atoms, which you go on to later, we'll know that that's right.
There is actually a shortcut, yeah. But this is just the empirical formula, like I say, it didn't really fit in quite nicely with last time's video.
But it's a quick summary. And now on to
Acids and bases. Alright, we've been doing this video for quite a while, and if you look on your pages in your textbook, relative to what we've been doing on the board, you'll notice
we've done 15 definitions.
15.
We've gone past them. You might have noticed we didn't say any of them.
We haven't said any of them. We figured you'd do that yourself. We're not going to go through every definition because what good is it us saying it to you when you have to read it yourself anyway? You have to do it over and over again. So
you need to learn it.
You need to learn it. How much is it worth, Triv?
It can be up to 40% of your exam, which can make you pass.
40%, that's an E on its own, just definitions. Most of them are 3 2-mark questions, and there's quite a few. There's quite a few. 40% is quite a lot.
That's a lot of the exam.
There's the difference between a top A and like a C. That's mad.
So you have to learn.
And how do you learn them?
Like this.
You remind me of a man.
What man?
Oh, the man with the power.
What power?
Say the power of voodoo.
Voodoo.
Yeah, you do, you do.
Do what?
Oh, remind me of a man.
What man?
Say the man with the power.
What power?
Oh, the power of voodoo.
Voodoo.
Yeah, you do, you do. Wake 'em, dick 'em, anonymous red. Save us from the man with the hex. Save us from this evil curse. It's gonna get bad, yeah, it's gonna get worse.
Go.
Wake 'em, dick 'em, anonymous red. Save us from the man with the hex. With hairy legs and heavy feet. He cracks up pavement as he creeps.
Firstly, what are they? What's an acid, Triv?
Well, an acid is a proton donor. What's a base, Wayne?
It's the opposite, it's a proton acceptor.
What are protons and what does it mean to accept and donate them?
Well, a proton is just simply hydrogen ion, H+, that is a proton, quite literally. Proton donor, it gives away its hydrogen ions.
Proton acceptor accepts them, takes them away.
So let's just quickly give a few examples of acids you'll come across in your AS. We have HCl, which is what?
Hydrochloric acid, didn't you see it? Hydrogen will be donated, and sulfuric acid, H2SO4.
So another example I'm going to do here. We have ethanoic
Ethanoic acid, which is vinegar.
So what we've got here, we've got hydrochloric acid, sulfuric acid, ethanoic acid. These two are strong acids. This one is a weak acid. What does that mean, and how would we know this? Let's get rid of some root.
Well, a strong acid does something that's called fully dissociating, and a weak acid doesn't fully dissociate. But what is dissociation? Well, it's when you get rid of this hydrogen plus ion, and a strong acid will do it really quickly, like this.
It strips it down into sort of, as you can see, you can sort of picture it as stripping it down to its bare minimum, the H+, the Cl-, and it does that really quickly, which makes it a strong acid. It's really corrosive, it's really powerful. It says, here, take my hydrogens.
Yeah.
Same with this one. There's actually two hydrogens given off, so it'll actually break down into this. We've got H2SO4.
Then goes down to
H+ again, except
two of them, and
plus
then
another ion.
SO4 2 minus.
And that's the exact same thing. It's stripped down into its two most simple ions, and it makes it really corrosive. Whereas this one, this is ethanoic acid, it's in vinegar. If that was strong, you'd know about it with your chips. What, what does this mean? What happens here? We have this equation.
What's going to happen here is not all of the hydrogen ions are going to split from the main thing. In fact, only one of them is, and it's called partially dissociating. And this means that reactions happen much slower. Like if you were to throw some magnesium in one of these acids, the same thing would happen. The magnesium would disappear, hydrogen would be released. But in these ones, it would happen way quicker than in those ones.
It's almost not even worth doing this reaction. Like if you do it in a laboratory, putting magnesium into an acid, you would do it with a strong acid, because that happens like that. It fizzes up, it heats up. This one, that could take you ages. I mean, if it's a weak concentration, that could take about an hour, whereas these ones take a few seconds. So that basically sums up the beginning of acids. We'll go on to the reaction to acids in a minute. Now on to bases. We're going to need a bit more room, so let's rub off this board and start from scratch. We're purely on bases.
Welcome back. I've got more room. Onto bases.
Up here we have the pH scale. You can see anything with a pH of less than 7 is an acid, and anything with a pH greater than 7 is a base. This should be revision from GCSE, but we've drawn it up here for you. So firstly, bases. What are they?
Well, they are proton acceptors.
Acceptors, indeed.
And a few examples of bases are
Magnesium oxide and calcium oxide. In fact, all metal oxides are bases, and bases will neutralise acids. You can sort of imagine a base as a pH of here somewhere and an acid here somewhere.
and when the neutralisation will pull them towards the middle and
Back to a pH of 7, hence neutralised, because this is sort of the neutral zone. But so these are bases. These are just two examples. Any metal oxide is a base.
we'll talk much about bases and we get to titrations and things like that.
This is just sort of the underlying knowledge, then we'll build up on it with reactions and titrations.
Yeah.
We also have something else called alkalis. They are a type of base, i.e. all alkalis are bases. It's just, this is sort of the general idea of anything beyond here, whereas alkalis are specific ones, and
They've got a property. They're a base that dissolves in water.
yes, and these are hydroxides. We have sodium hydroxide, NaOH. You could have magnesium hydroxide, Mg, and then in brackets, OH2. We also have ammonia, NH3. That's an alkali, despite it doesn't have the OH. It's just an exception you've got to know in your head.
A weird one, because nitrogen does strange things to hydrogen. We'll go into that quite a bit later.
Yeah. So hydroxides are alkalis. They're also bases, because all of these are bases, but alkalis are the
Not all
specifics.
bases are alkalis.
Yes.
Yeah.
So these break up into Na plus and OH minus.
And it's the OH minus, the bit that's alkali. This is because it's what accepts the proton.
So if I write it back up what we had before, there's my red pen. We had that HCl, an acid, hydrochloric acid, breaks up into H plus Cl minus. And what we said was it's all sort of revolving around this proton, because these are a proton donor, this is a proton acceptor. So this acid has donated, this base is accepting.
So look at like the base ionic equation for these reactions.
Yeah.
Basically what's happening is an H plus going with an OH minus,
It's going to form, as you can probably see, water, H2O.
and water is neutral.
Water
That's what we were
is
talking about before, going into the middle and making 7.
So these are the underlying rules of bases, alkalis, and we went on into acids before. Now we can move on to titrations and actually using
some of the
them
equations
in
of these.
reactions.
Let's crack
And this
on.
is
We're going to pretend there's an acid and here a base.
So what you'd actually do in the experiment, if we were doing this, which we can't because we don't have access to a lab right now, you'd twist this nozzle and you'd actually drip the acid into the conical flask with the base until the base has been neutralised.
But Wayne, how do you know it's been neutralised?
Well, we use an indicator. In this case, we would actually be using phenolphthalein.
I like phenolphthalein. Bit dodgy though.
It's a bit dodgy.
It goes from pink to pale pink,
Which is hideous.
which is hideous.
How do you know why it's
Tiles
pale pink? But yeah, what you do is you pop this phenolphthalein indicator into the base, and it will actually turn the base pink.
Yeah.
And you drip this in until it goes to pale pink, which indicates the end point, otherwise known as when this has been neutralised. This will have then gone to a pH of 7. So, and it will go on a point. I know, it'll be one drop,
one
and
drop,
it'll
and
go
it will change. Also, one more drop and it will go clear, which means
too far. You're
Takes
actually
too
going
far.
back the other way.
You
You're
would.
turning this acidic.
which is bad.
That's a bad. So what we have is we know the concentration of this acid. We know the volume of this acid, because that's what this works out. That's what the spirit is for. and then you can work out the moles. Then with stoichiometry, you work out the moles of this, you know the volume of this, you can work out the concentration of that.
Which would be our unknown.
That would actually be the question, yeah, what is the concentration of the base?
Of the base, and
So let's run through that quickly. So first we'll write out our equation, because that's always a good step to start with. What we've got here in this example is hydrochloric acid.
Are we going to react hydrochloric acid with magnesium hydroxide, which is an alkali?
And this will produce, I'll write it underneath,
Yeah,
NgCl2, which is magnesium chloride,
absolutely.
and water.
Also, very briefly, magnesium chloride is a salt,
It is a salt.
and we have definitions.
We'll come back to salt in a second, it is a definition, but this is a reaction you're going to have to know for your exam is acid plus alkali equals what plus what, which is in this case salt plus water.
Yeah.
So I'm actually missing something. I'll get the red pen.
Oh
By
yes,
stoichiometry you should actually have two
balance.
HCl's, because you see you've got Cl2, H2 to balance it, HCl.
Alright, okay. So let's actually do this experiment. Let's do it. Right.
Oh, whoa, don't do it quick. You've got to mix it.
Oh, yeah, okay.
I'll mix it.
Okay, great. Oh, I think that's about. I think that's power pink. All right.
So our starting titer in this case, we're going to imagine was 50 centimetres cubed, i.e. up here we had 50 centimetres cubed of acid. At the end, when it changed its colour, we're going to imagine we had 35 centimetres cubed left. So the titer is 15 centimetres cubed. You'll notice he put 0.00 on all of them. Why is that true?
Well, but you're at it reads an accuracy of 0.00. Also, when you're reading it, you need to watch this little ring we've drawn on the diagrams here at the top, called the meniscus, and it's a sort of dip in the water, and you've got to read from the bottom of this.
So what we have here, we have the volume in centimetres cubed. So let's draw out a table, because what we've got to do eventually is work out the concentration of this. So make a table, HCl and the other magnesium hydroxide. Now we want to divide this up into, rub this out.
Yeah.
We don't need this now. Moles, concentration, and volume. So we know the volume of HCl, because that's what was measured here, the 15 centimetres cubed we just did. But firstly we've got to turn that into decimetres cubed, because that's what the concentration is, moles per decimetre. Remember in the last video?
Oh. So divide it by 1,000.
So we actually get 0.015 decimetres cubed.
Absolutely.
Concentration of the HCl is known. It will be on the bottle when you put it into this burette, because that's how you need it. So the concentration is going to be 1 mole per decimetre cubed in this example.
Nice and simple.
Nice and simple. So then, with what we had in the last video, we know the equation for solutions. N is C times V. We know V, we know C. Let's work out N. I've got a calculator.
Oh.
Guess how much this was, Triv?
£50 quid. That.
Anyway, so we've got concentration 1 times volume, got 0.015.
You really needed the calculator, way.
It's
Wow.
0.015
Nailed it.
moles. I had to get my money's worth.
Oh, absolutely. We also know on this side is we know how much volume was in this volumetric fund.
We actually measure out the volume, and it's going to be 25 centimetres cubed, which you have to again have in decimetres cubed is 0.025.
Yes.
Little heads up actually, what they might do is say you've got 25 millilitres. Well, that is just 25 centimetres cubed. That tripped me up at first, of course. I was completely lost. Now, we're trying to work out this.
This is a big question,
The
man.
concentration of this. Now, for this equation, we need at least 2 of the things to be able to work out the third. So we need moles.
We do need moles.
And
now
how
we
do
have
we
to
do
call on
that?
our friend
We
stoichiometry.
mentioned it in the last video. What is it? It's the molar relationship. So, here, did it in a different colour for you. There's 2. Here is actually
There's a
there's a 1. So you have 2 of these, but 1 of these. To get from this to this, you half it.
You do. It's every 2 moles of hydrochloric acid react every 1 mole of that.
So you actually do the same thing here. There'd be 2 of those and 1 of those.
So we use that relationship, divide it by 2
Here to here.
to get.
I'm going to use my calculator again.
Okay.
Guess how much this was, Trivett? It was 50 quid. 50 quid. 1.015 divided by 2. Do you want to see?
Right. Oh, that's what I got in my head too.
Oh, this is good.
Pretty
50
pleased.
quid equals Triv's brain. So now we have the moles, we have the volume, we've got to work out the concentration.
So once again,
Rearrange this equation.
oh yes.
How do we do that, Triv?
Well, you wanted to get C on its own, so we divide both sides by V, so
That's right.
N over V equals C.
We know that N is 0.0075
We do.
and V is 0.025. I'm going to do this on my calculator. Guess how much this was, Triv? Oh, it was 25 quid.
I was using stoichiometry.
And it is 0.3, which is a good sign. 0.3 moles per decimeters cubed. That is the answer to the question.
And that's how many.
All titrations questions will be similar to this. Sometimes it might be the other way around. You might know everything about this and have to work out this.
Yeah, sometimes you'll you'll dilute something in a volumetric flask and you have to do a few more complicated things, but we'll try and do that in the lab if we can.
We'll do that in a lab for you. So that's one thing to take away from this, is actually the titrations itself is a unit. Now
Yes.
you know sort of what to do, what they are. We did it for you with the twisty.
No, yeah, very nice.
Like we said, we'll do it in an actual lab. But finally, you've got to know acid plus alkali equals salt plus water. We're going to go on to the rest of these equations.
Yes, and what a salt actually is.
And what a salt actually is, yeah. Let's move on to that right now.
Yes, crack on.
What's that?
Salts. Wayne, what is a salt?
According to the book, a salt is any chemical compound formed from an acid when a H plus ion from the acid has been replaced by a metal ion or another positive ion, such as the ammonium ion NH4+.
So I don't normally cover definitions.
You will actually have to know this definition, but let's just clear it up.
Yeah, we just want to mention it because it's quite helpful to explain.
We'll do it on this side, because you don't want to take up much room with this.
Yeah.
You've got hydrochloric acid plus sodium. We'll just go with sodium.
Yeah, just go to sodium.
Goes
Jump
to
out of the way.
sodium chloride. That is a salt. Why is that, Triv?
Well, it's because the hydrogen in the acid has been replaced by the positive metal ion, sodium. That's when you fish.
That's the same with all acids. A salt is just where there's been an acid and the hydrogen in the acid has been replaced by something like a metal ion or something
Yeah.
like that. So the definition makes it sound horrific, but it's actually fairly
It's pretty simple, yeah.
So I'll give you the rubber. You could pass that out.
Nice.
Rub that out.
That's I'll pass it out too. Just as we go.
So that was a salt. Now let's learn the salt reactions. How do you form a salt? Well, you do an acid plus either an alkali or a base or a carbonate. So let's go through these reactions now.
Well, salts here quite a lot with acids all the time. It's sort of acids and salts thing, they're very closely connected. So we'll
Acid plus carbonate first.
yeah, okay. So carbonate like magnesium carbonate, MgCO3.
Yeah.
Yep.
An acid plus a carbonate goes to what? This will come up in your exams, and if you just know this general rule of acid plus carbonate equals something plus something plus something, then you can work it out and deduce what it is when you're in the exam. So acid plus carbonate goes to a salt, what we just discussed, plus carbon dioxide, CO2, plus water, H2O.
Water appears for all of them, it's
Yes.
but carbon dioxide does not.
Yes, so this carbon dioxide is actually only for the carbonates. You've got to try and remember that.
It's not too hard. Carbon dioxide.
Yeah, you can sort of deduce it. Let's go for a second. We've got acid plus alkali, like what we just did in the titration.
Oh, lovely titration.
Lovely titration.
Magnesium hydroxide or something like that.
Goes to what? If you actually remember, we actually wrote out the equation here, and I said it to you just a few seconds ago. You should remember. It's a salt plus water. And again, that's something you've got to remember because it will come up in your exams.
Well,
Finally, an acid plus, what are we missing, Triv? Carbonate, alkali, just a base.
Oh.
So a base, in this case, is the ones that aren't included in the alkali, so it's metal oxides.
Yeah.
In this case.
Things that won't dissolve in water.
Goes to what? In fact, it goes to the exact same thing as this. It goes to a salt plus water. So perhaps we should do an example for each of these things here. Just a quick example. I'll get a different coloured pen. Have we got a red pen?
Have we got a green pen?
Oh, green pen will do. I like green. We'll go with hydrochloric acid for all of them. That's my favourite. That's not an L, is it?
No, it isn't an L. That's a C. That would be something
No,
else.
HCC.
Nearly methane, but not quite.
Plus a carbonate. We'll go with what example? Pick an example.
Magnesium carbonate.
Magnesium.
Magnesium's quite nice. I like the foily bits. They're quite lovely.
What makes a carbonate is the CO3, so you've
Yeah.
got something carbonate. Now in this case we've got magnesium carbonate, so what does it make, Trev?
Well, wait, I'm going to grab a
He's
red
gonna
pen.
grab a pen. It's going to make a salt, which we said is when the H of this has been replaced by the metal ion here. So we're going to have that Cl, because it's replaced this. It's going to be magnesium chloride, MgCl2. Again, you're going to have to take our word for it the second we'll move on to it. How do you know it's Cl2 and not just Cl? But plus carbon dioxide, CO2, plus water. And is it balanced?
I'm not sure it is. Wayne.
Not, is it? Well, we've got two Cls over here, we've only got one here, and we've got two hydrogens, and we've got one here. So we've got two in front of that, and that is in fact balanced now.
Beautiful.
Again, I'm going to use HCl because it's quick, it's simple, and it's my favourite.
It is quite a nice acid. One that's often worked with in coursework practicals.
What alkali shall we use?
I think sodium is
I think sodium is
quite nice. You get some table salts at the end for your chips.
Sodium hydroxide. Notice we don't need the brackets around the OH this time because it's not OH2. So we'll go on. What's it going to make? It's going to make a salt plus water. What's the salt going to be? It's where this has been replaced by the metal NaCl. We did that at the beginning.
Yeah.
It is salt, as Tripp keeps joking about. Then we have H2. Oh, it's balanced water. Finally, an acid plus a base. Again, HCl. It's my favourite.
This does seem quite boring, a bit trudgy, but
Yeah.
in pressure exam it's very useful to really keep remembering these rules because they do come up all the time.
And they can actually twist questions that come with this to make it seem more difficult. Whereas
Yeah.
if you know the general idea of what's going on, you can
Sort of pick apart
calm
the
yourself
question.
and
Yeah.
So what base shall we use, Triv?
Magnesium again. I like
I
magnesium.
like magnesium. It's a
Magnesium
good
oxide's good.
We'll go with magnesium oxide, and it will go to a salt plus water. The hydrogen's been replaced by a metal, so it's going to be MgCl2.
So again, it's not balanced.
It's not balanced. Plus water, H2O. You'll notice there's two of those. There's two hydrogens. You quite simply put a 2 in front of that. These are your general reactions to produce salts. Like we say, remember them all.
Yeah. Quite important.
Now we're going to go on to something called waters of crystallisation.
Ooh.
So
Let's crack on.
Alright, now we're on to something called waters of crystallisation. Probably going to be quite new to you. I don't think it's done at GCSE.
No, it's
so
a scary
It
phrase.
is a scary phrase. What is water of crystallisation, Triv?
Well, Wayne, basically it's the water or hydrated part of a compound. Like if we have copper
Copper sulphate.
sulfate, it might have a dot. If it was hydrated, it would have copper sulfate is, which is CuSO4.
So that's the copper sulphate part
Yeah.
with the water
And you
crystallisation.
have there a little dot, and then you write by number how many moles there is of it, and H2O. That's the water bit, and this is the water crystallization bit.
Yes, so it's, you'll know when it's dot X amounts of H2O
Yeah.
that it's a water of crystallisation question. But how do you know how many of these there are going to be? Well,
That's quite a big question they
that's
ask
a
quite
big
often.
question, and it is, yeah. We're going to go through an example that's actually in the book and sort of
Yeah.
explain it to you.
So,
Got to go get the book, I left it over here.
yeah, so Wayne's going to go get the book. So what we're going to do is going to work out what this is. We'll have other, maybe already unknown. There's two methods, we're going to go through our preferred one. Okay,
And
here
we're
we
on
go.
page 27 of this book.
Okay.
Worked example. So what do we have here?
Okay. Well, we have a hydrated salt. We have magnesium
Oh.
sulfate.
Magnesium sulfate.
Yep. With an X amount of H2O.
X amounts of H2O.
And we've weighed this, and we've come to the weight of 4.312 grams.
Come on, where's the board rubber? Where's the board rubber?
Board
Board
rubber.
rubber. I'm going to rub this out to get in the way a little bit. This is a whole new example.
Here's a whole new example.
So let me just go for this. 3, 1, 2.
You might do an experiment where you'll basically heat this and get rid of the water. And we've done that, and now we have a new weight without the water, which is 2.1. I'm getting there.
2.1.
07
grams.
grams.
7 grams. So we've evaporated the water away. When you heat it, you actually do this in your science lessons.
Yeah.
So you're left with just that.
So what we're going to do is we're going to
We can
find the
determine.
difference,
Yes.
and that will give us how much the water actually weighed.
So if it weighs this much with the water and this much without it, we can deduce how much
We can.
X amount
Bit
of
of
H2O.
Sherlocking.
Yep, Sherlock.
Oh.
So how much is that? Because that's maths.
Oh, I don't want to get the scary calculator out again. So it's 2.205 grams.
Right.
Okay.
So we're trying to work out X. Okay, we're trying to work out how many waters there are in this particular waters of crystallisation example. So Triv, what do we do?
Well, first we calculate the amount in mole of anhydrous without water.
Right, so we have N equals what, Triv?
Well, we have to work it out when.
No, I meant that's of a molar mass.
Oh, I see what you mean.
This is in the previous video. It was one of the molar things we went over. Moles equals mass of a molar mass. We did it in titrations. We used some of the equations. We're actually using it again now, but the solid version, mass of a molar
We are.
mass.
We need to work out the moles of this to start with.
Yep.
So-
Doing this one first.
We need to know the MR, and the MR of all of this is 120.4. That's just adding up all the different parts.
20.4.
And
the mass we know
we
is
know 2.107.
107.
And that equals 0.0175 mole.
So just to be clear, what we did here is we look at the periodic table. We went through it last time. Magnesium is 24.3. There's one of them. Sulfur is 32.1. There's one of them. Oxygen is 16. There's 4 of them. You add them together, you should come to 120.4.
Absolutely.
Mass of a molar mass is moles of this. So now
Yes.
we're going to do the XH2O.
Yes.
So
Calculate the amount of mole of water. So know the mass,
MR, we've got 2, lots of 1.
and
16.
16, so that's over 18. And that's 0.1225.
So we have how many moles of this, we have how many moles of this. Now we're going to do a molar ratio, like what we did at the beginning of this video.
We are, so we're going to divide both of them by the smallest number.
And the smallest number, as you can see, is going to be that one. So there's going to be one of them, which is good, that's what you want.
Yep. We're gonna-
So
Yeah,
divide that by the smallest.
and the bottom and the other one by the
It's going
smallest.
to be 1, and this one divided by the smallest.
It's going to be 7.
It's going to be 7. So what this means by molar ratio of that to that is there's going to be 1 lot of that in this, so that's 1, which is good. We want it to be 1.
Absolutely.
The X is going to be 7 because that's
Yep.
the ratio.
And
So
that's
let's
that
write this
ratio.
out. We have MgSO4 7 H2O.
And that's one of the methods of working out. There is another one where basically you end up finding out how much the MR of this should be, and then you just divide it by 18. But we prefer this method. I think it's
This
the better
method
one.
is simplest for most people, I think.
Yeah.
And this is waters of crystallisation, a whole new thing. You actually get some pretty crystals. You get
We do.
nice colours.
Often blue.
Often blue, I like blue.
I like blue. Yeah, I think now on to the next bit. Florio?
Because you're worth it. Alright, we are back with the last bit of the unit for
In the end.
Unit 1 of Chemistry AS.
Yes.
So we're on to something, again, new, so
Really exciting. Oxidation numbers. A lot of videos before we kept mentioning, we know that this equation is going to be this, we know that Mg is going to be OH, there's going to be 2 OHs. And this is to do with rules of oxidation numbers. It's not that we've just memorised every one in the world, they actually follow patterns. We can use the periodic table to work out this. That will cover stuff in a few seconds, talking about how earlier groups will be positive, later things will be negative, and basically oxidation numbers need to equal 0 in a compound.
So here I've drawn a very quick, very poor periodic table.
I think it's very nice.
I think it's quite nice. I've divided it up into the essential parts that follow the actual rules we're on about.
Put it into groups.
So we're going to start with group 1. Let's swap
swap sides.
So group 1 is here. We have sodium at the top.
Yeah,
there. We have lithium and stuff like that.
And these follow a pattern. They have one electron in their outer shell, and that basically means they're going to give an electron. So we know that to be a +1 charge. Everything when it's exposed to water, it'll be sodium plus.
Lithium plus. Hydrogen is actually at the top here.
Yes.
It's out of the periodic table, but it is in group 1. And this is what oxidation numbers are all about. It's how many electrons are there available for reaction.
Yeah.
So here we have plus. So let's go on to group 2. What's in that? We have magnesium in
We
there.
have magnesium, we have calcium.
Calcium. Goes down to stuff like barium and stuff like that.
Yeah, it does.
But we have group 2, and again it follows the trend. They'll all
does.
go to
Plus
+2
2.
because they have 2 electrons in their outer shell.
Absolutely.
Now group 3 is over this side.
Past transition metals, they're crazy.
They have their own special sets of rules. You don't really touch much on them at AS at all.
Really
Really.
do stuff, really.
It's not. You don't do much with them. So if we'll just blank this out in terms of oxidation. So go straight to group 3, where you have aluminium and boron.
Yeah.
So group 3, as you can imagine, by
Yeah.
following these rules, is +3. Now we're actually going to do a little bit of a jump to the opposite side, because it doesn't go +4, +5, +6, +7. It actually makes more sense to do it the other way around.
It does. So switch again.
Up this side we have the noble gases. Now they don't have any electrons free, so we're actually going to cross this one out as well. So we go to
Group 7, which are the halogens, so chlorine, fluorine, aspartame,
all
all
that
of
sort of
these.
stuff. Now instead of having a +7 charge, which you can think of it like that, it's easier to think of it as a -1.
Yes.
So opposite to this side,
That's
coming
what it is.
backwards.
There's a -1 charge.
And following the same pattern, we get -2 with the oxygens,
And then
-3 with nitrogen. And in the middle you have carbon and silicon. They do very special things we touch on in Unit 2.
we do.
And then we also touch on it later with organic chemistry. This is
So
essential for everything with carbon.
yeah.
But these are the rules: +1, +2, +3, -1, -2, -3.
As I spoke before, in a compound, well, not an iron or anything else, it needs to equal 0.
That's
So if we go for the example that we kept bringing up, you knew what magnesium was going to be. You knew that magnesium is in
Magnesium
group
is
2,
actually here in group 2, yeah.
so it's a 2+ atom.
Whereas we use MgCl, well Cl is here in group 7,
Yeah.
and that's -1. So to make this whole thing equal 0, you're going to need 2 of these to equal -2
You will.
to balance out the +2.
2 minus 2 is 0.
And that also, you can also work it out with ions using these rules. If you had MgCl, not MgCl2, you would have 1 positive charge left over.
Yeah.
And now this opens up lots of doors for understanding sort of why all the compounds you'll come across work and are not ions, like HCl. H is here, 1+, Cl is here, 1- equals 0.
Sometimes you'll encounter compounds with things that you know the oxidation numbers of, but then there'll be something that's sometimes a bit mental, like carbon, and it'll ask you, what's the oxidation number of carbon here? And you could work it out by using these rules.
You also get stuff like, we had magnesium hydroxide, remember? We did this.
You used to using brackets in chemistry.
Yep. Magnesium again, it's here. Magnesium is 2+. OH is actually a negative ion, but
It is.
if you want to think of it properly, you can think of oxygen is here, 2-, hydrogen is here, 1+. So altogether, OH is a negative ion.
Just -1.
So then you do the same as these rules, except it's not single elements, it's a complex ion like that. So you need 2 of these to balance the Mg2+.
You do. It's not just looking at compounds and working out how they work that oxidation numbers used for.
No. We have stuff like redox reactions, which we're going to go on to now.
Yeah. A redox reaction is where something called oxidation happens and something called reduction. Quickly rub all this off.
We'll be right back.
Now on to redox reactions. Redox reaction is where reduction and oxidation happen at the same time. But what are these things?
You might remember from GCSE something called oil rig. I'll put that up first, it might help you out in a minute.
Yeah, something that we use to remember, an acronym we use to remember what they actually meant.
So, oil rig, what does it mean? Oxidation is loss. So let's put that down. Oxidation is loss of electrons.
Ah.
And what does the rig stand for? True?
Well, reduction is gain, it means gaining of electrons. This is when they move into different shells between ionic bonds, is easiest to see.
And we just said a redox reaction is where both a loss of electrons and a gain of electrons take place. So let's do the example of magnesium plus chlorine. Chlorine is a diatomic, it travels as a two. Goes to, and this is what we just learned about the oxidation numbers. It will go to Mg, which is 2 plus if you look at the periodic table.
It is.
Cl2, because each Cl is just 1 minus. And this happens to be balanced.
It does. Before we start, when an element's on its own or just bonded with itself, like this chlorine, it doesn't have an oxidation, well it does, but it's 0.
That's right. The oxidation number here is 0, and here is 0.
So here is where we see oxidation and reduction happening.
When it's in a compound like this, we've just spoke about the oxidation reactions, that was the previous slide. This is 2 plus, this is 1 minus, there's 2 of them.
Yeah.
So you can see here that the magnesium to have bonded has to have become 2 plus.
Now what 2 plus actually means is it's lost 2 electrons, and as they got a positive charge, it's now 2 plus.
Now, if in a different colour, we can say that the opposite has happened for Cl. Cl it's gone from 0 here, it's now at Cl minus. So and we've got 2 of them, so that balances it out.
It does.
What does this mean? This means loss of electrons. Well, as Triv just said, because electrons are negatively charged. If you lose negative charge, you become positive, which is what the magnesium has done. So we can say that the magnesium has been oxidised.
Yes. And the chlorine has been reduced. Also, in A-level you have to speak about oxidizing and reducing agents.
That is correct. Let's get the book out. I'll just finish writing up what we were saying, and Triv will explain what reducing and oxidising is in just a second. So we've said the Mg is oxidised, the Cl has been reduced. It might actually help you in an exam to literally write underneath the oxidation numbers of the individual things in their compounds, and then you can see quite clearly what's changed and then in turn what's happened.
Yeah.
So, what are reducing and oxidising agents, Triv?
Well, when you think about oxidizing and reducing agents, you've got to think about what causes it to happen.
That's right.
So, more or less, you flip them. Mg is a reducing agent because it causes
The
chlorine.
Cl to be reduced.
Yeah.
This has inflicted upon that to become reduced. That means this must be the reducing agent.
And equally, the other way around. Chlorine has caused magnesium to be oxidized, so it's the oxidizing agent.
The way I actually do it myself in exams is I do it this way first. I literally write out what's happened, then I decide which has been oxidised, which has been reduced, and then I simply flip it to say which is the reducing agent, which is the oxidising agent.
I think that's the easiest way of doing it. You don't get confused about what caused what.
That's correct. Now there's also a special thing called disproportionation reactions. We've actually left a little gap here.
Yeah, it was planned.
It was planned. So Triv, you want to write up disproportionation reaction with a black pen?
Very much. Here's a blue pen.
Love blue.
It's a good
Now,
colour.
a disproportionation reaction is a redox reaction, but it's where both the oxidation and the reduction have happened on the same element. The example is normally chlorine, isn't it?
Yeah.
Chlorine normally goes from, 0, so it's just chlorine on one side, but it reacts with 2 things. So it becomes both a positive in one compound and negative in the other compound, because some elements actually have this property. So let's go through an example now. Right, so now we go on to an example of a disproportionation reaction.
This is where, yeah, both reduction and oxidation elements are the same element, as you said before.
So we have hydrogen peroxide
We do.
going into water and oxygen. We get two lots of that, as well as that.
Yeah. Okay, so first step is, I think it should be every time, split them up and write out what each thing is. The oxidation state. Here we can see it's plus. We know what hydrogen is, we know we work out what oxygen has to be for it to work. 1 minus.
Some elements have strange properties where they can actually be a different oxidation number to normal. So in this case, because you can see that the oxygen is in the second part twice, you know that's going to be the thing that's had both things happen to it. So you sort of have to deduce what's happening.
Yeah. And then moves across, break the H2 up. This is behaving more normally. So we have +1 for hydrogen and 2 minus for oxygen. And then we have an element. We know about elements, they're always 0. So
You can notice.
notice the oxygen goes from -1 to -2, and then -1 to 0.
So you can see here it's gained 1 electron to
Yeah.
become more negatively charged. So gain of electrons is reduction, so it's actually been reduced from here to here.
It has
Then the opposite.
been oxidized. It has gained charge.
There you go, it's lost an electron because it's gone up in charge.
It has.
So the oxygen has been both oxidized and reduced, so that's the same thing has had both happen. So it is a redox reaction,
Yeah.
but it's a special type that makes a disproportionation.
It does, and in the exam, or often exam questions, basically they give you quite a big area of almost like an essay type question. They go, what is being disproportionated? Yeah, I think that's the right word.
That's the right word,
Yeah,
disproportionated.
that works fine. And show why, and you basically have to show the state changing. It going from,
You normally get a mark saying that from -1 to -2 in this case. Basically you get a mark for saying from this to this is this, either oxidized or reduced. Then the alternative, we go from this to this is the opposite. And then third mark for saying this makes it a disproportionation reaction,
yeah.
which is a redox reaction.
And that pretty much covers oxidation and
And in turn, the entire Unit 1 of chemistry. Wow. So
that's quite a lot.
let's discuss what we've been through today. Right, we're here to sum up what we've done in the video today.
Rid of that.
I
No.
found it.
It was quite exciting.
So,
What did we cover
I
in?
can't remember what we even started with now.
Well, very briefly.
Oh,
It wasn't the end of Unit 1, it was Module 1, Wayne's.
yeah, wrong choice of words. We haven't finished Unit 1, not
That would be incredible,
We finished Module
We did
1
fun.
of Unit 1.
of which there is a few more than one.
Yeah, so wrong choice of words. But we started off with the simplest whole number ratios of stuff. So
We
that's
did. Empirical formula.
mass over. What do we do it over? Jesus, it's been so long.
Grams of it in the compound, is that right?
No, that's the mass.
Oh, that's so then the MR.
MR. Yeah,
There you
that's
go.
it. I forgot the word MR. And that gives you moles, and then you find the relationship.
The ratio.
Relationships.
Stoichiometry. Yeah.
Then what did we move on to? Jesus.
We moved on to acids and bases.
Bases and what they are. Acid is
Yep.
a proton donor,
And a base is a proton acceptor.
and an alkali is a special type of base that dissolves in water,
It
forming
does.
OH minus ions.
Ooh.
Ooh.
Uh,
We actually went straight from there into titrations, didn't we?
We did,
It's
so
not
we had-
quite the order in the book, but it makes more logical sense.
I think it makes more sense then to go on to the equations.
So titrations, you have a burette, you drip it into the base
Yeah,
until it's
swirl it.
until
Yeah.
the end point that determines.
Yeah, we used
Yeah,
phenolphthalein, but there is other indicators. You
There's
use
methyl
methyl
orange,
orange, which
and
goes from red to orange. Is
Yeah.
it? Yeah.
Well, it depends if you put it in the acid or the base, because sometimes you can do it the other way around.
You
have the
could.
acid in the bottom and drip base into it.
That's more unusual then.
That's more unusual, as normally the acid is in the burette.
They went
We
on
did
to-
that, and there you can sort of see the relationship and how important stoichiometry is in terms
Yeah.
of titrations, at least.
And they went on to, well, salts.
Yeah, we went sort of back in terms of the book, but forward in terms of logic
Yeah.
to what salts are.
And all, how acids quite like salts. They appear all the time, and all the equations you need to know.
So, Triv, acid plus carbon, what does it make?
Well, it makes salt, carbon dioxide, and water. Wayne.
It's the only one that makes carbon
It
dioxide.
is here, it's carbon dioxide. Wayne. I forgot everything. I did.
Sound like centre.
An alkali plus an acid.
An alkali plus an acid goes to a salt plus water, and
does.
from there you can sort of guess, but an acid plus a base.
Hey, you drop the base and it.
Salt plus water.
Yeah, there's like a salt plus water.
And you've got to know them, well.
Yeah.
From that you can deduce what's going on in a lot of questions. It's
You
really
can,
good, really
yeah.
useful.
There's a lot in the coursework bits.
We then went on to waters of crystallisation. Was that next?
I think so, yeah.
Yeah, waters
Yeah.
of crystallisation, nice blue crystals.
Yeah, well, if you use copper, being the hydrated part of a compound, and then working out the X bit, how many moles of water is actually in it.
You normally have X amounts of water, and your challenge is to work out X.
Yeah.
That's nearly always the question you get with them.
It is, isn't it? Both exams and coursework.
And your coursework. So you just evaporate this water away and see the change in mass, and then you can deduce the mass of what this water is.
And then,
When you know the mass of how much this bit weighs, you can deduce how many lots of this you have by a molar ratio again.
you can.
Then what do we move on to next was oxidation numbers.
We did.
We're
just
piling
covered-
through this. We're piling
Yeah. Covering what oxidation was.
through.
Loss.
And the idea of the periodic table, and you can see +1, +2, +3, and then -1, -2, -3.
Yeah. Now every compound has to equal 0, so you can work out what oxidation numbers should be.
Yeah. And we then went on to redox reactions with the oxidation reduction, which uses the oxidation numbers we'd just done before then,
Yeah.
but yeah, it does.
Let's know what an oxidation agent is
Yeah,
and a reducing agent.
And a special type of redox reaction, disproportionation reactions.
It's a good word to use.
Unfortunately there you find out that some of the elements don't actually fit the periodic table
Yeah,
rules
they
we had.
do break, but normally there is something that will fit the rules.
And you can see if there's like we have the oxygen was the thing that was disproportionated
Yeah.
because there was different. It was twice on the other side, whereas nothing else was.
Yeah, and generally when that
So
happens,
deduce
you can see that that's going to be the element that is.
that is changing and not
Yeah.
obeying the rules. So you can see hydrogen is going to just be +1. That's not going to change
Yeah.
for this example. It doesn't change at all, hydrogen, but
Yeah.
that's how you'd be able to tell. And yeah, I said Unit 1. It's actually just Module 1. Unfortunately, we've still got
A lot to do,
a
I
lot to
think.
do. We are currently
Module-
here. We're on Module 2,
Yeah.
electrons, bonding, and structure.
Ooh, we get drawn. Is it skeletal things in this one?
No, that's miles ahead. You're miles way up here.
I am way up there.
We have
ahead of myself.
a little bit more about shells, orbitals, which sort of solidifies some of the oxidation numbers
Yeah.
we did. There's
What
a
it
lot
actually
of
means
use.
by lossing, losing,
Yeah,
and gaining.
rather than just learning them, you're actually using them here. Then we go into the different types of bonding and stuff, which we actually spoke
Yeah.
about in the first video, as we said we'll come on to later. We have the shapes of ions. You actually start to learn about what they actually look like
Yeah,
in
their 3D
three-dimensional
structure.
space. Then we have, well, it's all about structures after there very much. Electronegativity and polarity links directly into it.
Yeah, a bit about dipoles.
A bit about dipoles.
And
And that's Module 2. We'll get on to Module 3 when we get there, but yeah, we've done Module 1, we've done quite well. Again, we've rushed it because there's so many things that
Yeah.
different people might struggle with.
so if there's
Everyone's
anything that a particular question, put it in the comments below and we'll try and find time to go through that question, or maybe send you a link to a different video that explains it.
Yeah, because we're literally just covering up
Yeah.
basics.
Yeah.
This
I
is
think
Wayne
that's-
Lack and James Trivett.
Until next time.
Let's crack on.